After the fork and the pipe, let's consider the collider as a reason why OLS regressions may confuse you when it comes to the interpretation of causality. Some people, when they run regressions, have the tendency to throw in all the explanatory variables that they have in their dataset. And the idea is that they want to be safe from any problems related to a fork. So they want to control for every variable that they have. But as the collider example shows, this actually also can cause confusion. And it's not a very good idea. So when you choose the variables that you want to include in your regressions, make sure that you have a model in the back of your head that suggests why these variables should be there, what the story is of these variables affecting your y variable. So the collider example that we're going to be looking at is given by this picture. So we're interested in the effect of education of children. In particular, we know, and we're going to hard code this in the data, that the parent's education has a positive effect on the child's education. So we're going to be coding a positive effect of the grandparent's education on the parent's education, and a positive effect of the parent's education on the grandchild's education. And the thing that we're interested in is that controlling for parent education, is there an additional effect of grandparent education on the grandchild's education? Yeah, so a potential mechanism might be that the grandparents every now and again babysit on the grandchildren, and they may transfer knowledge then. So the idea is to run a regression of the grandparent's education on the grandchild's education, controlling for parent education. And we're going to see that this regression throws up some results that at first sight are very confusing. So we're going to model the fact that grandparent education has a positive effect on parent education, and parent education has a positive effect on grandchild education. But another effect on a child's education is the neighborhood of where the child grows up. Yeah, so that's modeled here with neighborhoods effects, and we're also going to hard code this in the data as well. So the idea is that if you live in a good neighborhood, you have good schools, and that improves the education of the child. If you live in a bad neighborhood, the schools may be less good. The friends that you play with might stimulate you less to improve your educational achievement, and therefore there might be a negative effect of such neighborhood effects on the education of children, and in particular the grandchildren. So now let's code our data. So here we're going to have more observations than we did up till now, so we're going to model this for number of observations of 5,000. Alpha is going to be the effect of the neighborhood, and I'm going to set it equal to 0.5. Then X is going to be the grandparent. So the grandparent's education is modeled as a draw from a normal distribution. And we're going to draw a number of observations out of this distribution. So this is going to be the grandparent. This is going to be very similar, so it's the neighborhood effect. So this is going to be the neighborhood. And this is going to be the parent's educational achievement, so that depends on X, which is the educational achievement of the grandparent. So there's a strong positive effect of the educational achievement of the grandparent X on the educational achievement of the parent. Plus we have our neighborhood effect, plus a noise term that I'm going to multiply by 0.4. normal size, oops, wrong bracket, number of observations. So this is the parent. So now let's line out this a bit. Okay. And the next line is going to be very similar, so I'll copy paste it. So here we're going to have the educational achievement of the grandchild, which depends on the educational achievement of the parent. And also here we have this neighborhood effect, and we have this random effect, and this is the grandchild. Yeah, so the educational achievement of the grandchild is positively affected by the educational achievement of the parent, and the educational achievement of the parent is positively affected by the educational achievement of the grandparent. Both these educational achievements of the parent and the grandparent are positively affected by U, which is the neighborhood effects. And just to be sure, there is no direct effect in the way we coded the data here of grandparent education X on the educational achievement of the grandchild. There is an indirect effect via Z, but there is no direct effect. So we're going to put this into a data frame, which we call Collider. Data frame, so we're going to provide a dictionary. So column X, column Y, column Z. So this is the data frame that can actually be observed. We're going to assume that neighborhood effects are not observable, but later on, if you want to check the outcomes of our regressions, you may want to add this additional column just to see what the regression does if you can also control for neighborhood. But we're going to assume that neighborhood is not observable to the econometrician, so we leave that variable out of our data frame. And just to make sure that we have the data frame that we expect to have. Yep, so that works. So I have 3 columns, X, Y, and Z, and these are the first 5 rows of my data frame. So to start with, I'm going to run the regression of, so I'm going to call that results, again using stats models, OLS. So we're going to run the regression of Y, so that's the educational achievement of the grandchild, on the educational achievement of the grandparent. This is the thing that I'm interested in. And I'm controlling for the educational achievement of the parent, C. Then my data is data frame, Collider. I want to fit this. And then what I'm interested in is the summary of this regression. So let's run this. So what we see is that the effect of the parent's education on the education of the child, so the grandchild, is positive, as we would expect. The thing that's odd here is that the grandparent has a negative effect on the education of the grandchild, and this negative effect is highly significant. However, nowhere in the data did we include or did we code a negative effect of grandparents' education on the educational achievement of the grandchild. So the question is, what does this coefficient mean? Where does it come from? And again, the point here is that there is nothing wrong with the OLS, so the math is working perfectly fine. This coefficient is correct, but it's just hard for us at first sight to interpret what it says. Because the thing that we coded all along was that there is a strong positive effect of a parent's education on the educational achievement of the child. So there's a positive effect of the grandparent's educational achievement on the parent's education, and there's a positive effect of the parent's educational achievement on that of the grandchild. So how on earth can we get a negative coefficient here, that there is a negative effect of the grandparent's education on the educational achievement of the grandchild? So one thing that I leave for you to do for yourself is to run the regression of y on x directly without including z. That already gives a first idea of what's going on here. But to get an intuition for this negative coefficient, we're going to actually plot the data. So what a multiple regression does is it looks at the effect, in this case let's say the effect of x, controlling for z. And controlling for z basically means keeping z constant. So how can we visualize that effect that we're going to keep z constant? We're going to do that as follows. So I'm going to define a Boolean mask, which is equal to df collider. So I'm going to look at the z variable, and I'm going to focus on values of z that are close to 0. Yeah, so the absolute value of c is going to be smaller than 0.05. Yeah, so you can do this for other values. So if you want to compare it to 1, so you only want to consider values of z that are close to 1, you can do it as follows. But here I'm going to focus on the case where the values of z are close to 0. So I'm going to define this mask, and I'm going to use this when I'm plotting. So first, let's make a scatter plot of our data. Oops, df collider.x, df collider.y. I'm going to label this, label this as all data. And then I'm going to have labels on the x-axis, the x label, which is education of the grandparent. Yeah, so that's the thing that we called x, and then the y label is going to be education grandchild, which we denoted y. Oh, let's make this consistent. So we're going to get PLT legend. We're going to have PLT. Oops. So here we have a scatter plot of all the data, and the thing that you can clearly see is that there is a strong positive correlation between x and y. And the reason is clear. The more educated the grandparent is, the more educated the parent will be, and this higher education of the parent will cause a higher educational achievement of the grandchild. So we have a strong positive correlation here. Now we're going to do the same scatter here, but only for our selection. So they're using the Boolean mask. So again, here we also use the Boolean mask, and the label is now data with the absolute value of z, the absolute value of z smaller than 0.05. Yeah, so in orange we have the data for z that is close to 0. So the orange data gives us the slope of our multiple regression. This is the slope for x that we get when we control for z, meaning z is kept constant. In this case, z is kept close to 0. Yeah, but you can plot it also for other values of z, being close to 1 or being close to -1 or whatever. And you see the same negative slope, but then at a different level. In fact, in the Jupyter notebook that we use in class, we create an interactive graph where you can vary the level of z by dragging the data around. So now we have a negative correlation in orange between the education of the grandparent and the education of the grandchild. And the interpretation for this is the neighborhood effect. So all observations here in orange have very similar educational achievements for the parent. So when you look here at the grandparent who is highly educated, but the parent was sort of averagely educated, it must have been the case that this grandparent was living in a bad neighborhood. And this bad neighborhood negatively affects the educational achievement of the grandchild. Now consider, for instance, this point over here. The grandparent was not particularly well educated, but the parent was, because we're still focusing here on this group of parents with the same or similar educational achievement. So how is it possible that this parent, who was not very well educated him or herself, had a child, the parent, who is pretty well educated? It must have been that this family was living in a very good neighborhood, and that very good neighborhood also positively affected the educational achievement of the grandchild. So the negative coefficient that we find in the multiple regression basically reports on the neighborhood effect. It says that the effect of the grandparent's education, when I control, so when I fix for the parent's education z, is the neighborhood effect. And that means that a grandparent which is very well educated compared to a grandparent that is not very well educated, while their child, the parent, is equally educated, that means that this grandparent with high education was living in a bad neighborhood, and this grandparent, who had bad education him or herself, but the child had the same educational achievement as the very well educated grandparent, this grandparent here was living in a very good neighborhood, and that very good neighborhood positively affected the educational achievement of the grandchild. So I leave it to you to check this story by redefining the data frame, including the variable u, so including the variable on the neighborhood, and then running the multiple regression, including the neighborhood effect. Yeah, so this is in a sense cheating, because in the real world you may actually not have this neighborhood effect variable. But here, just to check that the story that I'm giving you is correct, you can run the regression by including also the neighborhood effect, and then see what comes out of it. But the overall conclusion here is that the idea of just throwing in any variable that you may have at hand to control for all other effects is actually not a very good idea if you don't go through the reasoning of how that variable might affect the y variable that you're interested in. Yeah, so in this case, if I look at the education of the grandparent and I control for the educational effect of the parent, suddenly the neighborhood effect becomes important, which is something that I may not have thought of when I put that variable in the first place. And therefore I will be surprised by the negative coefficient that I find in the multiple regression.